Okay, so we're doing another video. This is actually a tutorial video on specialist maths in the vectors two-dimension chapter. So actually this is chapter 3b. I'll change that. And we're going to look at part B, geometric vector operations. And I'm going to start by going through the general operations, and we'll have a look through the textbook, and we'll do some questions together. All right. So in the previous lesson, we looked at how we could express vectors in terms of these arrows, which have a certain length and a certain direction. Now, for the sake of that, I've got an arrow, that's our vector A, and I'm going to look at that carefully and say that is 1, 2, 3, 4 units up and 1 unit to the right. So I'm going to say that is 4 up and 1 right. Now, that notation I'm writing there will come up in a future lesson. All right. But we won't worry about that right now. But that just helps at this point when we're drawing these. So this one, okay, so it's on B, 1, 2, 3, 4, 5 to the right, and no movement vertically. So we have those two. All right, so we're going to go through a few operations. I'm going to run through all the operations that you need to know for chapter B. There's a number of subchapters in here, but we'll look at all of them. So chapter 3b, we'll go through all the parts. Okay, so first skill you have to know is vector addition. If you're adding two vectors, the way to do that geometrically is to draw the first vector and draw the second vector from the end of the first vector. It's what we call tip to tail. And then you can actually work out the resulting vector. So I'm going to do that. So if I was to add these two vectors, A and B, all right, well, my first vector was 1 to the right and 4 up. So if I pick a point to start, so I pick here. Actually, I'll pick there. So if I draw a vector that's 1 to the right and 4 up, it will look something like this. Now, see, it's a little bit longer than it should be. I'll put a little arrow in that. Okay, so that's A. All right, then I'm going to draw B. B, this is 5 units to the right. So now I'm using 5 millimeters squared, so that'll be 2.5 across. I'll just count 5 squares to the right, and you've got it. That's B. All right, so then what is the vector addition? Well, I'm going to take out a different color. I haven't tried it. This one hasn't worked in a while, but take a risk. All right, there we go. So that is my resultant vector. So I drew it in a different color. That is A plus B. Okay, so I've now added those two vectors. This is important for things like some of forces in physics and other things. I'm thinking physics, obviously, because some of you also do physics if you're studying specialist mathematics. But whenever you see vectors add, yeah, that's how you go about doing it in a geometric sense. Now, subtraction. Fun enough, we're not actually going to minus the vectors, we're going to add them. But we learned something in the previous lesson. A negative vector is the same vector in the opposite direction. So if we were to add A plus minus B, we'll just draw B backwards. So A minus B, the way that we carry out this operation is we actually draw A and then we add the negative of B. So what would that look like? Well, let's give ourselves a bit of space. Okay. So A was 1 across and 4 up. As such. Okay. So that is A. Now minus B. Well, if B went 5 to the right, then minus B will go 5 to the left. So again, add that. So you've added minus B. See there. So we've gone A plus minus B. All right, and our resulting vector goes from the start of the first to the end of the last, just like the other one. All right, so that is now A minus B, as such. And that's how you carry out vector subtraction in geometry. All right, you might also be asked to do scalar multiplication, and this could be used in conjunction with anything else. So you might be required to halve a vector and then add it on to something. Whenever you do something like halving vector, I was thinking about doing another operation, but I didn't have enough space for it. So, and also I didn't pick the nicest numbers to work with. So if I was to halve that, half A, well, you know what? No, I'm going to double A because I just realized that if I halve that. So I'm going to rub that right out. Let's do, I'm going to do 2A. I'll draw it somewhere else. Okay. Let's get another. No, let's use the space we've got here. I'm going to do, let's just go through. Minus 2A plus minus 3B. All right, what would that look like? Well, think of it this way. 2A minus 2A plus negative 3B. Well, I'm going to draw a vector that is now Ka multiplies the length of A by a factor of K, so this is going to double the length, but for K equals 0. So just a reminder that the negative changes the direction. So I'm going to go, if I started here, I should have enough space for that. Let's not do that. Let's do, I'm going to rub out the 2. There we go. So minus A and minus 3B. So that means I'm going to go 1, 2, 3, 4. I'm actually going to go down and to the left. So down and to the left. I'm free-handed drawing that. Okay. And then B, I have to go across 15 squares. All right, so might as well get my thing out for that. Because that would be that long, I believe. So that was minus A. As minus 3B. So I've taken, sorry, let me show you that. I've taken B 3 times the length in the opposite direction. And that would be the resultant. Okay, and there we go. Now, in general, when you add vectors, the order doesn't matter. The diagram will actually look different. If you were to draw B first and then A, or do you go across and up? But if you actually worked out how many squares right and up, both of them would be the same. There are reasons why you might choose to do it one way or the other, and they have to do with what you measure off when it comes to working out the direction of the vector. That's for another lesson. Okay, so those are the 3 skills for the first section. A couple of things that comes up early on. There is a form of vector algebra where you have a start and end point. So instead of writing like lowercase vectors, you write coordinate points and you draw a vector at the top. So it means this is the vector that takes us from A to X. And we're going to add the vector that takes us from X to B. Well, in vector addition, as we've seen, so say if I had coordinate points, so I say that was kind of X, Y, and Z, then the vector from X to Y, add the vector from Y to Z, just takes us from X to Z. And that is what we see in the algebra. A to X plus X to B is A to B. So if you see this Particularly if you ended a point and you started that point and moved somewhere else in the vectors, then you can just kind of cancel the x in that sort of way. Say, okay, well, what I've done is I've moved from A to B because, okay, they end and start the same location. All right. Now, the last little part of this subchapter goes through vector equalities. Vector diagrams that are closed, so there's no open gaps, so closed polygons, can be expressed as vector equations. And the way you do this, you follow the tip to tail vectors, and they are the sums. I should say vector sums. So if I look at this diagram, all right, something plus something equals something, because I've got 3. Now, if you look at the way this is, I've got a tip to tail from A, then B. So I'm going to say A plus B. Is there another way to get there from A to B? Well, yes, there is. There's C. There's just one vector. So thereby, you start and end at the same point. So then A plus B equals C. And that's what you got there in the vector sense. Okay. So here we've constructed something a bit different. So you've got 2 vectors coming off this point here. So you got A and C. But I could say A plus B takes us from that point to that point. But so does C plus D, because they're in there, they're arrows. So I can say, okay, A plus B equals C plus D. That's how you do vector equality. So you're looking for patterns of like vectors that are adding, and you end up going to the same place as you do at the end. Now, there's another way to approach this where you kind of just follow it around the circle. I might demonstrate that in a future question if it comes up. So let's have a look at some of the work you have to do for this chapter. So you can go through the examples yourself and go through the steps. Follow their examples. You're welcome, if you've got an online version, to look at some of the demos. But yeah. The other thing as well, zero vector. That's one thing I actually didn't mention. If you end up with a vector, like for example, if you subtract a vector from itself, you end up with what we call zero vector. So that means it's a vector of no length. We'll come to that again later on. All right. So, and here we see some practice of this simplification of vector addition. B plus C and C plus A is BA. B to A plus vector E, A to E is, okay. Plus E to C, sorry. So you simplify that. BA, AE, that takes you to BE, plus EC is B to C. So you can see, because you're stopping and starting at the same points, you've got that. A plus B, B plus C, C plus A. Now, if you end up back where you were, that's a zero vector. You do good closed body. And the last one, AB plus BC plus CD plus DE is A to E. All right. So let's have a look at some of the other ones we have to do. Okay, I think these drawings are pretty straightforward. So you know what? I'll get rid of that. Let's get some graph paper, so I might do some of them. Okay, there's the graph paper. So I might pick 1 or 2 of these to do, take my interest. All right, so if I was to do 1A, put some light on subject, a bit better. Okay, 1A, if I add those two, that's my P. So I've gone 3 up and 1 across to the right. And Q is 2 up and 2 across. All right. And that vector there is P plus Q. Okay. If they fall over the top of each other, like an E, because it looks like P could be expressed as Q because it's like half the length in the opposite direction. That one's going 2 across and 4 up. First one. Draw that. So that's P. Now, if you want, you can draw it in a different color. Maybe I will. For the sake of this, what colors do I have? I've got blue. Do I have black? I probably don't. Oh, I have a 4 pen. Let's just hope this works. Just so I can see it over the top of it. All right. So yes. So you can see, you might be able to see the green there. That was 1. That's 1, 2 down and 1 across. So that was Q. Okay. Then your resulting vector P plus Q is actually this. So you go from the start of the first to the end of the second. So P plus Q is that little vector going up there. And that shouldn't come as any surprise to those who've done physics, yes. If you've got vectors traveling in opposite directions, or vectors have components in opposite directions, adding them will result in a smaller value. So yes, adding in vectors can get smaller numbers. And that's what we saw here. All right, so moving on. Okay, so I might take some, I'll take 2F. So 2F. All right, BC. Let's see, BC plus CA plus AB becomes, all right, BC. If I just take the first two, I'm just going to do this in a couple of steps. BC plus CA is BA. All right, now that's going to be the zero vector. Why? Because BA is minus AB. And you see, and also you see in some of the examples that simplification is B to B, which means you haven't traveled anywhere. If you haven't traveled anywhere, you've got a length of 0. So think of it that way. Length of 0 means 0 vector. All right. So, all right. And just point out 3B is true. You can draw it 2 ways. You end up basically just drawing. So if I drew any 2 vectors, I'll do 3B. We're not exactly proving this for all values, but I'm saying if I draw a vector like this, that could be my A. That's my B. So I just picked those randomly. That went up by 1 and 1, 2, 3, 4, 5, 6, 7 across. And that went 1 across and 1, 2, 3, 4, 5 down. All right, the resulting vector now, what if I did it the other way? Just to demonstrate, I'll start at the same point of drawing that space. I could draw it separately and it will just end up being 2 parallel lines as a resultant vector. But what if I drew B coming off that point there? Well, 5 down and 1 across. There you go. That's the first one. And then so that's B. And then, okay, funny enough, 1, 2, 3, 4, 5, 6, 7, and 1 up. then that's b plus a. Same thing. All right. So I might leave that one as a challenge question. You can try that yourself. All right, geometric vector subtraction. Okay, you can have a look at those examples, but that's how they go about it. Okay. Okay. I'll do one for question. Okay, so now we look at subtraction, question 2. All right, so if I do R minus Q minus P, I'm going to write that as equal to R plus negative Q plus negative P. I do that out of habit. Okay, so R takes me, R, Q would then be up and P would be that way. So I'm going to start over this side. Actually, I'll draw it underneath. A bit of space. Okay, R is 3 to the left and 2 up. Stop from there. Sorry, I haven't done that. Well, no, that's 3 and 1. My bad. Okay, I need to draw somewhere else. Okay, draw on the side. Over here. That's R. Q, it would be 2 up. Minus Q, I should say. Because Q is 2 down. Minus Q is 2 up. And minus P. P goes 1, 2, 3, 4 across, 1, 2, 3, 4 up. This goes down and across by 4. Okay, so then that's a resultant of R minus Q minus P. There you go. Okay, I will also do one of these ones. I might take 3F. Okay, so the way to go about doing these ones, just remember, if you've got subtraction, you're changing the direction, which means if you have coordinate points like this, DC, you can just swap them around and just make an addition. So the negative going from C to B is the same as going from A to B, A to C rather. And then you've got, okay, swap that around, D to C, C to D rather. Then that equals, well, you've gone from A to B to C to D. AD. There you go. Okay. Vector equations. All right. So the suggestion there, we select any vector from the left-hand side and then take another path from the starting point to its finishing point, and then that's equal. Yes, that's true. One way to think of it. And there are some examples of that. So I'm going to do a couple of examples of that over here. Maybe making this a bit of space. Let's do a bit of space here. Vector equations. So let's have a look at these ones. All right, so I'll pick a simple one to start off with. Let's do B. B. All right. Now we can see in B, we've got two vectors that are tip to tail. Actually, I could write there's a few ways. Okay. Actually, they're all tip to tail. A couple ways we could do it. Mind you, here's an example of what I was thinking of before. Two ways I can think about that. If I go R plus S, like that, so I go R plus S, well, that takes me in the opposite direction of T, so I can write that as minus T. Another way, if you do have a closed object, but you follow the directions and it takes you in a full path through, you could say that R plus S plus T equals 0. Because that's true, because you end up back where you started. So thereby that's a zero vector. Okay, so that's two ways to think of it. Okay, so I'm going to look at E. So let's look at the tip to tails. Now you can see there's two vectors coming off this point, so I'm going to treat them separately. So let's go from P to Q, so P plus Q. All right, so let's start there again. See where the other side takes us. T plus S plus R takes me to the same place. So P plus Q equals T plus S plus R. You start and finish at the same point, therefore, those vector additions are equal. Okay. So, all right, so this is sort of skill breaking things down, which is actually necessary for some of the vector proofs. Once we kind of worked on these skills, this will be second nature, and be able to work this out. All right, so I'm going to take 2b from that section. All right, so looking at this diagram, I've got a vector a to b equals p, and b to d equals d, and d to c equals r. So let's find a to d. What we're going to do is find a path that goes from a to d through different steps. So I don't have a labeled vector for that. But if I go somewhere else, maybe I go from a to b, and then from there from b to d. Let's write that out. A, b, plus b, d. Well, I have vectors for those. AB is P, and ABD is Q. There you go. All right. So that's B part 1. What else? B to C, part 2. Or B to C. Well, that I could write that as Q plus R. It'll take me from B to C. B to C equals, I'm just going to write that, Q plus R. All right. Part 3, AC. So A to C. A to C. Okay, we can go to A to B, B to D, and D to C. We can actually go use one of the vectors we worked out before, though. So we could go AB, then BC, because we worked that out. Basically, or if we go this way, A to B, B to D, D to C. That's P plus Q plus R. But I'm going to check that by doing the other way. A to B, then B to C, because I worked out B to C in the last question. Well, A to B, A to C is what we're working out, equals A to B plus B to C. Well, A to B is P, and B to C is what we got here, plus Q, P plus Q plus R. Well, that's what I thought it would be. So there you go. All right, so that's how we do those. Okay, I think this might be the last part, geometric scalar multiplication. So yes, just remembering that if the number you're multiplying your vector by is a negative, it will swap the direction as well as scaling it up or down. So you can see some examples of operations here. All right. So if I was to do, maybe it gets a bit more space. I do, okay, 3b4 questions, I'm going to go, I'll do a simple one. I'll do B, question 1B. So 1B, 2S. Well, S is 2 down and 3 to the right. So if you do 2 of those, 1, 2, and yet you can draw 2 vectors of the same length and then just say SS is 2S, thereby 2S. That's fine. Let's take something a bit more challenging. H. Let's go for the last one. Okay, half of R plus 3S. Well, I'm going to expand that for the sake of drawing it because it's easier to do the addition that way. Half R plus 3 halves of S. Okay. So if I draw half of R, that's unfortunate. That's what I was trying to avoid in my one, because R goes, as you see this over here, where my mouse is, to the right 3 up, or that would be 1 to the right and 1.5 up. So something like that. That's unfortunate. Oh well, half R. Not that. And okay, then we've got 3 halves S. So S is 3 to the, yeah, it's going to get messy. So 3 halves, 3 to the right, times by 3 is 9 divided by 2, 3 halves, it's 4.5. 1, 2, 3, 4.5. Put a little point there just for reference. And down it goes 2. Divided by 2 is 1. Times by 3 is 3. So 1, 2, 3 motions down. So that little spot in the middle of that group there. So then that is 3 halves S. And then you got your vector sum. Okay, 1/2 R plus 3 on 2S. Okay, as such. Okay, so, all right. Okay, and that's the end of that. Maybe I'll take one of these last challenging ones. All right, so turn my page over. Let's do one more question. All right, what shall it be? What shall it be? Let's do 5. Why not? So maybe I'll do this on the note paper because I don't have to waste that then. Nope, I'm going to do it here. Okay, never mind. All right. So, okay, we've got vectors P to Q and Q to R. All right, as A and B respectively. All right, find in terms of A and B, Px. Now, can I find an alternate path from P to X? I believe it's inferred that there's parallel, so thereby, yeah, if you actually do work out that it is parallel, because the idea that is parallel. Basically, TS is parallel to A and UR is parallel to TS, so you can prove it. I don't think we have to go and prove it. We're just going to treat it. It's a regular hexagon. That's a different branch of mathematics to prove the parallel rules, but we'll get to that in the vector sense as well later on. So the idea that Px is parallel to QR, and also these vectors are equal in that sense. So that's equal to B. There's part 1 on part A. Okay, so what else we got? PS. All right, so PS is twice the length of that. So you see all these side lengths are the same because it's regular, and all these diagonal segments are also equal in length. All right, so as such, so we get that QX. All right, Q to X. Now this one we'd actually have to find a path to get there. So Q to X. The Q to X could be written as Q to A, then as A to X. All right. Sorry, what am I doing? Q to P. I'm getting ahead of myself. I'm thinking about vector A and then P to X in terms of the points. P. All right. So Q to P is negative of P to Q, which is negative A. I'll just write negative A. And P of X we actually worked out in part A, which is B. So minus A plus B, or B minus A, is the same thing. The last one, R to S. R to S. Okay. From R to S, we can see a path. We actually know how to get around here. And then there's this. And P to S. I've already worked that out. Okay. So I can actually write that. So I can take another path where I go backwards. But let's use what we learned with equalities. PQ, vector PQ plus QR plus RS equals PS, which I already know. And I know the other ones. So let's just work it out that way. All right, so PQ plus QR plus RS equals PS, which I know. All right, so then PQ equals just A plus B plus RS, which is the one I want to solve for, equals 2B. All right, so if I bring those across, RS can be written as minus B, so B minus A. Now, is that right? Q. Oh, yeah, that makes sense as well. That's the same as the answer for part C, which makes sense. They're supposed to be parallel. Well, there you go. We found it by different means. Okay, we're not going to let this video drag on anymore. Please go and do all the questions up to page 73 for this week. All right.